Have you ever had one of those days where you look up and just 2 hours of scrolling TikTok have completely vanished?
Oh, all the time. Or you're streaming a new show.
Exactly. But
Yeah,
then, you sit in traffic for 20 minutes and it feels like you've aged a decade.
right.
It's that crazy distortion where the clock on the wall and the clock in your head are just completely out of sync.
Well, that tension is one of the oldest mysteries in science. We talk about physical time, what the Greeks called chronos, which is that linear, uniform tick of a clock,
The boring one.
the boring one. And then there's experience time, or kairos, which is totally subjective. It speeds up, it slows down.
And for centuries, the assumption in neuroscience was that the brain must have some kind of single dedicated clock to process time, right?
A master clock, yeah, ticking away somewhere deep in the cortex.
But our deep dive today is looking at new research that says that whole assumption might just be wrong.
Precisely. We're diving into a really powerful perspective article in Nature Reviews Neuroscience by György Busaki from NYU.
Hmm.
And he basically argues that the whole search for a centralized brain clock is flawed because, well, it probably doesn't exist.
So the mind doesn't sense time.
It senses continuous change. That's the key.
Okay, let's unpack that. Busaki is suggesting that our subjective sense of time, my personal timeline, my kairos, it isn't housed in some special time region of the brain.
No. He says it's an abstraction. It's rooted in the constantly changing physiological state of your entire body.
So my body is the timer.
Your body is the timer. And to even begin to grasp that idea, we have to look at how we even structure time in our minds.
Right. And before we even get to neurons, it's fascinating that the way we think about it, past behind us, future ahead, that's not universal.
Not at all. It's completely culture dependent. The source material has this great example.
What is it?
The Aymara people, an indigenous group in the Andes. In their language and concepts, the past is actually ahead of them.
Way ahead. How does that work? The future is what we move toward.
Their logic is really pragmatic. They say, we have seen the past, we've experienced it, so it's visible. It's right there in front of us.
Ah.
But the future, we haven't seen it yet. So it's unseen, it's behind our backs.
Wow. So right from the start, time is tied to space and what we can physically experience.
Exactly. It's linked to memory and position.
Which brings us to the next problem, duration.
The feeling of how long something takes. If time were linear, you'd think 10 seconds would feel exactly 10 times longer than 1 second. But it doesn't, does it? It absolutely does not. And this is where psychophysics comes in. Busaki emphasizes that the brain's internal timescale is logarithmic, not linear. It's related to something called the Weber-Fechner law.
Okay, so a logarithmic scale. What does that feel like in the real world?
Think about it like this. You can tell the difference between a 1-second event and a 1.1 second event pretty easily.
Sure.
You have that same level of accuracy distinguishing between a 10-second event and an 11-second event. Your brain isn't measuring the flat difference, it's measuring the ratio of the change.
Ah, I see. So as time stretches out, you need a bigger and bigger gap to even notice a difference.
Precisely. That's why last year can feel like it happened 5 minutes ago. But the last hour feels so distinct and stretched out. The ratio of change is everything.
Okay, so let's go back to that classical search. Neuroscientists were looking for a literal single clock.
A metronome, basically, something that ticks uniformly and feeds its ticks into some kind of accumulator mechanism that just counts them up.
Like a stopwatch in your head. It sounds so simple, but they never found it.
Nope, total bust. They looked everywhere. What they found instead was this idea of degeneracy.
Degeneracy.
It just means that timing isn't centralized, it's redundant. Many different brain circuits can do it, so if one fails, others can take over. It's like having backup generators all over the place.
And that leads us to the hippocampus, right? The memory center of the brain and these famous place cells and time cells.
Exactly. Researchers found some cells fire when an animal is in a specific place. Those are place cells. And others fire in a sequence over a specific duration. Those are the time cells.
So it seemed like the brain had separate coordinates for the where and the when.
That was the assumption.
Oh.
But this is where Busaki's argument gets, it's really radical. He says, we're just labeling the same thing 2 different ways.
What do you mean?
He argues the neurons are just encoding one single thing, a continuous unfolding trajectory, a storyline.
So the cell is just firing as something changes.
Right. And whether we call it a place cell or a time cell just depends on what tool we, the experimenters, use to measure that change.
So if I use a ruler, I call it a place cell. If I use a clock, I call it a time cell.
You've got it. Distance requires movement, and movement takes time.
Mm.
In the brain, they're not separate variables. The trajectory is the reality. Time is just the abstraction we create from it.
So if there's no central clock, we still need a mechanism. What's measuring all this change?
This is the new paradigm, a brain-body hierarchy. The timekeeping is managed by a whole hierarchy of interconnected rhythms from the brain and the body.
Like a symphony orchestra.
That's a great analogy. You have this huge dynamic range of scales, from super fast to incredibly slow, all working together.
But how does the brain organize all that without a conductor? It sounds like chaos.
It uses a really elegant mechanism called cross-frequency phase amplitude coupling, or nesting.
Okay, nesting. Break that down for me.
Imagine a really slow, deep brainwave, like a delta wave, cycling maybe once a second. That's the phase. It sets the broad tempo, like a calendar.
It's the anchor.
It's the anchor. And the phase of that slow wave controls the strength or amplitude of much faster rhythms, like gamma waves, which can cycle 50 or 100 times a second.
So the slow wave is reading the fast waves.
It's essentially accumulating the information in the faster rhythms. It's a biological accumulator, not a digital one.
Okay, so we have these nested waves creating our sense of time. But where do the slowest rhythms, the big calendar waves, actually come from?
And this is the absolute core of the whole thesis. This is the most surprising part.
Okay.
The longest, slowest rhythms aren't all generated deep in the brain. They come from the body itself, from our autonomic and metabolic systems.
Wait, what you mean like non-brain systems are setting the master timeline?
Yes, absolutely. Think about your stomach. The contractions that regulate digestion, they run on cycles of about 1 minute.
So my gut is telling my brain what time it is.
It's feeding that slow temporal information back to the brain. And here's where it gets even weirder. Your heartbeat.
My heartbeat. Go on.
Studies show that your judgment of how long something lasts is actually contracted. Time feels shorter during systole. That's when your heart is actively pumping blood.
And what about when it's relaxing?
During diastole, when the heart is filling, your duration judgments are expanded. Time feels like it's slowing down.
That's incredible. So my sense of the present moment is literally shrinking and expanding dozens of times a minute, just based on the phase of my own heartbeat.
It's a continuous, closed-loop feedback system. These brain-body oscillations are a coordinated, distributed mechanism. They provide the raw data that the brain then abstracts into the feeling of time.
This explains so perfectly why time feels so warped so easily. If it's tied to our physiological state, then anything that alters that state should distort time.
And that brings us to dopamine. If you take a stimulant, or you're just really excited, you increase dopamine activity. And the research confirms that causes duration overestimation.
Overestimation, meaning my brain feels like it packed more events into a minute than actually happened.
Exactly. More neural activity, more internal ticks happening faster, so the physical minute feels shorter. Time flies.
And the opposite for something like alcohol, which slows the system down.
You got it.
And this has huge medical relevance in the US, right? You mentioned disorders that affect dopamine.
For sure. We see this in conditions like Parkinson's disease or ADHD. These are disorders that affect the basal ganglia, which is a key region for motor control and reward, and it's heavily run on dopamine.
And patients with these conditions often report a very altered sense of time.
Their altered time perception correlates directly with their dopamine activity. It's more proof that our internal clock is physiological.
So if the brain first learned about time through physical movement, through speed, Busaki makes this amazing point that running a speed is the evolutionary precursor to attention.
That's a fantastic way to put it. When we're deeply engaged, our attention is high, our internal speed is high, the rate of change in our neural state is rapid, so time flies.
And when we're bored, low attention, low internal speed. Time crawls.
Because almost nothing is changing internally.
Which is why, when we're stuck in that traffic jam, we unconsciously try to hack the system.
How so?
We create what the paper calls duration boundaries. We check our phone, we fiddle with the radio, we scratch an itch.
You're forcing new events to happen.
Yeah. Exactly. We're trying to force the system to register change, just make time speed up.
And if you look at the brain regions that are constantly tracking these body states, meta-analyses point to two main hubs for time perception: the insular cortex and the supplementary motor area, or SMA.
Let's break those down. The insular cortex is like the brain's internal dashboard, right? It handles interoception.
That's it. Interoception is that subconscious sense of your internal body, your heart rate, your breathing, that feeling in your gut. The insula is what makes you feel embodied.
And the SMA.
That's all about planning and sequencing actions. Planning to reach for a cup, planning to speak.
So the two main hubs for time are tracking the state of our body and our plans for action.
It's powerful validation for the whole idea. Time is an embodied relational and physical experience.
This deep dive has completely shifted how I think about, well, reality. Let's try to distill the three big insights here.
Go for it.
First, and this is the most profound one, we don't sense time directly. We only sense change. Time is an abstraction we create from that change.
Second, your internal clock isn't one thing. It's a whole hierarchy of brain-body rhythms running on a logarithmic scale. And its slowest anchors are things you never notice, like your gut and your heart.
And third, time warping isn't magic. It's quantifiable. It's a direct result of changes in your physiological state and your level of attention, or what we're calling internal speed.
And if you zoom all the way out, the article makes one final point. Without our human-made tools, our clocks and ruler space and time might just revert to being dimensionless concepts. They're human inventions, really.
Which leaves us with a pretty provocative thought.
Let's hear it.
If your most fundamental sense time itself is constantly being tracked and manipulated by the phase of your own heartbeats or the contractions of your gut, how much of your lived reality is truly under your conscious control?
Something to think about the next time you're bored in traffic and you reach for your phone.
Thanks for listening. We'll see you next time for the next deep dive.